What are the ideas behind the evolution of our comprehension of space, shape, and the impact of brilliant minds who reshaped the very landscape of mathematics with their groundbreaking concepts? What exactly is curvature and why is it so important? How do surfaces twist and turn in the world of differential geometry? Well, today we embark on a remarkable journey facilitated by a powerful tool, an exceptional book. Well, this is just not any book, it is a key that will unlock the world of differential geometry for you, making it not only accessible but also embarking on a fascinating adventure. This is not just a book, remember, it is a kind of a time machine that takes us back and introduces us to visionaries like Gauss, Riemann, and others, and explores the very essence of curvature, surfaces, space itself. Within these pages lies a treasure trove of knowledge that promises to make learning differential geometry an engaging and illuminating experience. It is not just about understanding history, it is about mastering the concepts with ease. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to lesson number 20, Curvatures, Surfaces and Genius Minds, where we are going to look into one of the best books to learn the origin of differential geometry. Like any other subject, first we need to know that why at all do we need to understand the evolution and history of differential geometry, rather not directly going into the problems of curvatures, surfaces and tensors. Coming in the next part of the video, I will tell you that why do you need to understand the history and evolution of differential geometry. Now you see, in the historical context, learning about the historical concept in which differential geometry emerged helps you to appreciate the problems and challenges that the mathematician faced during that time. This can enhance your understanding of why certain concepts and techniques were developed. The second thing is that you see, differential and geometry, it is all about applying calculus and bridging the gap between geometry and calculus. So knowing the historical connection between these two branches of mathematics helps you to understand that how the geometric ideas were combined with the powerful tools of calculus and to create a new field. We also come to know the early pioneers like Carl Gauss, Bernhard Riemann and many others, and to grasp the foundational ideas and theorems that laid to the groundwork for modern differential geometry. A brief understanding of the early pioneers of differential geometry will certainly help you. Most important, the development of curves and surfaces. Now you see, the understanding the historical development starting from Euler's work on polyhedra, Gauss's theorema egregium, which is called the remarkable theorem. All this, the curvatures, the measurements, it actually helps you to understand that why do we learn the curves and the surfaces and everything. So if you go back, understand the history, understand the evolution of ideas, development of curves and surfaces, and the complex mathematics becomes much easier. We also see there's something called a geodesic and a curvature. So learning about the historical development of geodesics and curvature measurements, including the contribution of Gauss and Riemann, helps you to appreciate the fundamental concepts that underline the modern differential geometry. Also, development of notations. You see that in differential geometry, especially in tensor calculus, there are what we call gymnastics of indices, something going up, something going down. So the history of differential geometry includes the development of notations, symbols, and familiarity with the evolution of the notations will help you to connect with the subject's symbolic language and better interpret the mathematical expressions. The connections to other mathematics, because history of differential geometry will let you know how closely they are intertwined with the histories of other areas of mathematics, for example calculus, topology, algebra, etc. So by studying the history of differential geometry, you can identify these deep connections and get a better understanding of mathematics. For example, understanding the historical development of tensors, which I have showed in my last video, can help us to understand how they used to unify different concepts of differential geometry in the areas of mathematics. and to gain a deeper understanding. So how the concepts of differential geometry have evolved over time, we can develop a more nuanced understanding of them. Studying the different definitions of curvature that have been proposed over the centuries can help you to understand the different aspects of curvature. Lastly but not the least, there is a huge connection, a very deep underlying connection with physics, because we all know that in the context of general theory of relativity, exploring the historical development will provide insights into how mathematical ideas were applied to solve real world problems. And finally, cultural and social context actually helps on the historic development of differential geometry, and it will help you to understand on a broader perspective on the interplay between mathematics and the world at a large, and it will help you to get a more enriching learning experience. So these are basically a kind of a motivation, a kind of an understanding that why do you need to understand differential geometry, more importantly the evolution and the history. And here is a quick summary. So the history of differential geometry offers some multifaceted perspective. It not only enriches you in learning but provides you a context and motivation to highlight the intellectual journey of creativity and the mathematicians who contributed to its development. Now, before we go ahead into the books, explore what is the name of the book, what we are going to do, here is a quick note on something very important. Now you see this video which I made, lesson number 18, how to learn curves and surfaces, and this video, beginner's guide to manifold, you can go into it, because it is a kind of a historical perspective and it will guide you more on learning manifold and curves and surfaces. Here you see that why you should study curve, why curves are important, which book to read, and a detailed review of the book that I have talked about you can find in this video. Also here you will find that why do we need the manifold. Surfaces and manifold. Are manifold only found in mathematics or in other areas? What are the surfaces which are considered not to be a manifold? A kind of a historical development, understanding, interpretation, and what would be the best book to understand manifold. I've given this. So before we go ahead, just a quick recap. These are very good and very important videos in your journey of differential geometry. So first we understand which book to read on the history of differential geometry. Okay, so the book name is by Professor Jeremy Gray, and its name of the book is Worlds Out of Nothing. Now you see below it is written a course in the history of geometry in the 19th century, but it speaks more about differential geometry rather than Euclidean geometry. The Amazon rating more or less tells 57%, 5-star. I think it should be more. And this is the photograph of Professor Jeremy Gray. Now before going ahead, let us understand who this person is, because as I told, when we are reviewing and understanding a book, who the writer, his authenticity, etc. is important to learn. Coming in the next part of the video, a little bit about Professor Jeremy Gray. So here it is. He has studied at the University of Oxford from 66 to 69 and then went to Warwick University obtaining a PhD, and he worked at the Open University since 1974 and lectured in the University of Warwick from 2002 to 2017. Now the most important and beautiful fact about Professor Gray is that he has written a lot of books other than that, and you will be surprised to see these are all related to the history and evolution of mathematics. Here is the first book, The Real and the Complex Analysis, History on the Analysis. That means it's basically a book on the complex and real analysis, how it started. It's a wonderful book. I think you should go through, those who are learning real analysis. Before that, a study about the history and the origin is a must. Second, Simply Riemann. I have not read the book, to be honest, but I really want to read this book. This is by Jeremy Gray on the life of Bernhard Riemann. Here is another book, A History of Abstract Algebra. This is a wonderful book which will give you right from the beginning how abstract algebra has been developed, who are the pioneers, and how the formulas and complex mathematics slowly got into it, and changes and variations. This is a wonderful book on the history of differential equations, how it all started. And apart from those 4 books, this is another great book, Jeremy Gay, about Henri Poincaré, a scientific biography. This is about the life of Henri Poincaré, which you can go through. And I think this is also, I just went through the table of contents, a wonderful book. So from this we can understood about the authenticity, the validity, and how wonderfully he has written all those books. So his profound influence on the books are mostly about the historical development. So no doubt this book which we're now going to go through is quite convincing that Professor Jeremy Gray is a master in this field. So a quick fact about that book, because this is quite a remarkable book which I told right at the beginning. First is that you see this is actually a book, Worlds Out of Nothing. This is the course, first book to provide a complete course on the history of geometry, especially in the concept of duality and non-Euclidean geometry. 3 chapters are devoted to writing and assessing works in the history of mathematics. And here I have also learned a wonderful lesson, which I'm going to just give you a brief overview. So 3 chapters for those who are writing or assessing the world on work on the history of mathematics. Examples, sample question. This is really wonderful. I will just tell you what it is. And the final part of the book considers how projective geometry as exemplified by Felix Klein in his Erlangen program of Euclidean geometry, looking into Poincaré's ideas about non-Euclidean geometry, and concluding with the formalism of Italian contribution and Hilbert's Grundlagen der Geometrie, that is the foundations of geometry. So this is a very special book which not only teaches you about the history of differential geometry, but also helps you to assess how will you write if you are validating something related to the history of mathematics. Really wonderful. So here we go. What are the reviews in Amazon? Let me tell you quickly. So this is exactly what it promises, blah blah blah, a history of geometry. So this is really wonderful. Good history, especially on projective geometry. And this is interesting. I'm actually reading this to gain insight to those who phrase all those things. So more or less the reviews are quite positive, and now it is the time that we should look into the content part of the book. So what are the topics that are covered? Now you will see, before I go to the topics, this is something very important which the author, Professor Gray, has pointed out. Now you see, this book offers a number of unfamiliar ways in which mathematics can be thought about. Now it actually shows its relations to philosophy and to physics, and noted at times explicitly discussed. That means Professor Gray tells that because this book is about the mathematics but not about mathematics course, so original motivations matter, individuals' critical judgment matter, and forming an overview matters. That means quite a different way of looking into mathematics. He also points out this way right at the bottom. You can see, in a much more modest way, a book that invites you to think about how imperfect judgments can most reasonably be formed as certain justification. This is really wonderful. So right at the beginning of the book, he points out that this is not a book about mathematics, but a book about the history of mathematics, and in a very non-conventional manner. Here is something important. You see, he has pointed out this book, Mervyn Greenberg's, whose Euclidean and non-Euclidean geometries I warmly recommend for its many insights from the standpoint of modern geometry, has spurred me in numerous ways to consider. Now, this book about Mervyn Greenberg's Euclidean, non-Euclidean geometry, I have given a complete detailed, I would say, book review, analysis and everything in this lesson of mine, lesson number 14, which book to start with, introducing differential geometry. You can find it on Physics for Students playlist of introducing differential geometry. I would recommend those who are willing to go from Euclidean and just started the journey to move into non-Euclidean geometry, please go ahead with this book. This is absolutely a wonderful book by Mervyn J. Greenberg, and you can see that Professor Gray also has recommended about this book, Euclidean non-Euclidean geometries. I warmly recommend, and I've already made a detailed video, lesson number 14. You can go ahead with that. So what are the topics that we are covering? It is very chronologically designed. As you can see, it starts with the French Revolution and the mathematics, Poncelet's pole and polar, then it goes into theorems in projective geometry, Poinclair's treatise, then it goes into duality, Poinclair's and chisels, then it goes to Lamberg and Legendre, and then it finds into Gauss. Further, it covers areas like from 1855, Bolyas and Lobachevsky, then the writing part, then the Mobius strip, the barycentric coordinates, etc., the duality paradox including higher plane curves, then Plucker's formula, which includes the real bitangents, higher plane curves, homogeneous coordinates, then it goes into complex curves including Riemann's publication and Riemannian geometry. Further, it covers concepts into differential geometry on surfaces, geodetic projection, non-Euclidean geometry is now accepted, I mean to say sequentially, then again the writing and the fundamental geometry. Finally, it covers about Poincaré's disk model, which includes Poincaré and Beltrami disk, the geometry of space, and finally the summary, the geometry from 1900. So it summarizes everything. Finally, you can see this is something which is written how to write assessments, how the essays will be graded, and the appendix, bibliography, and index. So what you can understand from this is that it is a very, I would say, sequentially and chronologically designed so that it starts from the French Revolution and ends around 1900. So it is a complete journey through the history of differential geometry. So I would now cover the overall content of the book, because as far as I remember, I think the book is round about plus 400 pages, which would take more than an hour if I go for a very detailed review of the book. I will cover the more or less the overview and the basic important concepts coming up in the next part of my video. So first, as you see, it starts with mathematics in the French Revolution. It starts with Mong's descriptive geometry. It gives you an idea about Mong and everything. And the figures, I would say, they are very nice. It is not that the printing is very bad. So all these figures, three-dimensional, two-dimensional, from Euclidean to non-Euclidean, has been very clearly laid out. All the indices, everything has been mentioned. Next, it starts with Poincaré's pole and polar, and here why the author has given much more emphasis on Poincaré's, because he is considered to be one of the founders of modern projective geometry, and projective geometry is actually the study of geometric properties that are invariant under projective transformations. Now you see there is a very subtle, I would say a subtle similarity between projective geometry and differential geometry, because in differential geometry our basic aim is to make the mathematics invariant under transformation, and it starts with Poincaré's. There also the study of geometric properties are invariant but under projective transformation. So projective space as an extension can be considered into non-Euclidean spaces, number one. Second is that the perspective and visualization in non-Euclidean geometry first started with Poincaré's projective geometry, how things are projected from this angle, that angle. So understanding of Poincaré's geometry is extremely important, and it is also a first step, I would say, to generalize the geometry and the algebraic structures. So this is actually what Professor Gray covers in the second part of the book. And then it gives a detailed idea about this treatise on the projective properties and figures. Why it has done so? Because from Poincaré's standpoint, during those days, every conic section is equivalent to a circle, what he thought. So his treatise contained a unified treatment of the theory of conic sections. These conic sections are further extended in differential geometry, as you all know. So the pole, polar, and duality, and the concept of duality arises from this. Next, we go into chapter 4, which covers of the theorems of projective geometry in a very, I won't say in a very detailed mathematical way, but in a very historical and chronological way. Here you see in chapter 4, he covers about Poincaré's treatise, which convey about singular claims, etc. Chapter 7, we are already into Euclidean geometry, parallel postulate, work of Lambert and Legendre, and we find these are the concepts. Euclid's Elements, a set of books he covers then about Lambert and about Legendre, and how Legendre took the opportunity to extend it further, and Lambert on the consequence of non-Euclidean parallel postulate. So you can say more or less from chapter number 7 we are all ready to move into non-Euclidean geometry. Here comes the Prince of Mathematics, Carl Friedrich Gauss. So he has given a kind of an idea about Gauss's differential geometry, about Schweikhart's square, and the details on the right hand side. I know a little bit hazy because I've taken an excerpt from the book. So that is about chapter 8. From chapter 9 we go into Janus Bolyai, and these are the figures. As you can see, these are beautiful. So Bolyai is L curve, Bolyai is F surface, and the fundamental figure where Bolyai first claimed that my geometry is going to expand and can answer all these questions. So Janusz Bola's new geometry has been quite well dealt in this book. Next we deal with Lobachevsky. Obviously can be considered as the first stepping stone into non-Euclidean and differential geometry. It gives a complete idea about Lobachevsky's. Here, what I was talking about, there's a great lesson to learn. I'll just take you a few minutes to explain all that. Now you see what he writes here is very important. He writes that the opinion that good historians simply tell us what happened in the past is hopelessly naive. Arguments on opinions and judgments play an inescapably large role in writing the history. One cannot look off the different views of historians and pretend that somehow one will transcend these and reach to the current opinion. The necessity of argument arises in the first place because the historical record is imperfect. Now this is truly important, because whether you are writing a mathematical proof, whether you are writing a real analysis proof, or whether you are writing a proof based on the history of differential geometry or any mathematics, you should understand that the historical record is imperfect. So he writes that much of it is lost, much of what exists is often difficult to access. Yeah, because it is written in different languages and stored in remote archives, and or hidden among a morass of too much of information. What survives and is ready may be wrong, even deliberately wrong. So this is something important. The history that we read today, or the history when what we are reading today and what you might be writing as a proof, are deliberately wrong. Because the historians and the historical facts are imperfect, because it is stored in archives and it has got perverted used by usage of different languages. So here he writes a very important thing. The problem of evidence is particular problem for the non-specialist, especially the beginner of the student, who simply do not have the time to browse among whose piles of material and depend naturally and rightly on the work of established historians, but relying on the expert. Another problem opens up. What is and can be only as an opinion become an established fact. So what is your opinion? This is my opinion that this book is great or that book is great, right? But this becomes a kind of an established fact, which is not right. And on the right hand side, I will like to show what Professor Gray tells, that this is his advice. When you are asked for an opinion or judgment as how important this or that is, try to give argument on both sides of the question and at least consider stating an opinion and only to disagree with it. Distinguish between contemporary criticism and someone's work and your own judgment. You will probably find it helpful to break your essay into parts corresponding to the various parts. So you may find it helpful to write notes. Try to use not more than 150 words. Each note should be one sentence long, and so on. So I'm not going to the subtleties of the advices that he had said, but this is most important because most of the historical records are imperfect, much of it is lost, and because somebody's opinion actually becomes some kind of a fact. And that is what he's telling in advice, that try to give arguments on both the sides and do consider and distinguish between contemporary criticism of someone first and your own judgment. This is truly awesome. I just thought to give you an idea on how to write anything of a proof driven, or even if you write history of a particular subject. So let us go back what we are left. So chapter 13 starts with Mobius strip and Mobius across the Rhine. Chapter 14 deals with Plucker, Hess and the higher plane curves. Chapter 16 deals with the mathematical theory of plane and curves. And then from chapter 17 we go to complex curves. Chapter 18 has been dealt quite, I would say, intensively, because Riemann is my favorite. I went through that subject. It covers about the vital points of Riemann's lecture and the book which I have cited in many cases, I think in differential geometry, general theory of relativity, everywhere, the profound mathematical genius who gave birth to the concept of manifold and other ideas on the hypothesis which lies at the base of geometry. So he has elucidated much more on Riemannian geometry in this typical chapter. So now you see we are directly into the evolution and how things have started to flow. Differential geometry of surfaces, Beltrami, Felix Klein's acceptance of non-Euclidean geometry, Hilbert and his foundations of geometry, followed by Henri Poincaré's disk model, and is the geometry of space Euclidean or non-Euclidean, and so on. So I have just taken the most important parts of this book. Okay, so finally we come to my honest review, and I would like to give you a very unbiased review of this book. First is that what I consider this is one of the best, easiest and most comprehensive guide where you can learn the entire evolution of geometry, especially differential geometry and non-Euclidean geometry. But here is a point. I found that the book emphasizes too much in certain areas about projective geometry. I don't know, maybe projective geometry or Professor Gray thought that it is important to know more about projective geometry, but certain cases it seems to be too much on that. A compact, and you will see there is a complete chronological order sequence of Euclidean and non-Euclidean geometry. You learn a lot of limitations, yes, because each theory, each I would say formulae actually gave rise to some kind of a limitations. Obviously then the new formulae, new theories or new concepts came in. So what were the limitations and then the solutions? And finally this one, I would consider this is the best guide to learn about the mathematical geniuses whose efforts actually gave rise to those ideas which culminated, and whatever we are studying today, you and I, are basically these people are the mastermind. So it becomes a kind of a moral duty also to know about a lot of those people, the hurdles, the complexities, the bottlenecks that these people faced and how they overcome. So this is my honest opinion about the book. So I would like to thank you very much for watching this video. If you like the video, please hit on the subscribe button, click on the bell icon to get all the notification from Physics for Students. You can always write to me on my email ID, and you can like my other channel on General Theory of Relativity. You can further follow me on my Facebook, Instagram, LinkedIn and Twitter account. Do let me know how do you like the book review and what is your opinion about the book. And Physics for Students will be soon back with lot of more excellent and good surprises. Till then, goodbye.